pharmacists and physiologists. This video is all about the respiratory system. Today we're talking about gas exchange. Let's recall that the main thing that the respiratory system does is that process of respiration. The last video in this series talked all about pulmonary ventilation, the act of bringing air into and out of the lungs. But this video will talk about the rest of it. So we'll talk about external respiration, which is the exchange of oxygen and carbon dioxide within the lungs at the level of the alveolus. We'll talk about transport of respiratory gases, and then we'll also talk about internal respiration, which is just the dropping off of oxygen to the tissues and getting rid of CO2. And as a reminder, the goal of the process of respiration is to deliver oxygen to the tissues, get rid of CO2. That's the big goal there. But before we jump into that, we need to understand some of the properties of gases. I've titled this slide, What's the Deal with Gases? Because they behave kind of funny because of some of their properties. Okay, so the first thing that we need to talk about is Dalton's law of partial pressures. What Dalton's law tells us is that individual gases, they all live in a mixture, like they're not just by themselves. And each of those gases within that mixture exert their own pressure. But then the sum of those pressures is the total pressure. So what I'm trying to say is if we have a container of gas, each of those gases are going to fill a certain amount of that container. Maybe it's oxygen, maybe it's nitrogen, maybe it's CO2, maybe it's something else other. And each of those gases exerts a pressure. If we were to add up all of those pressures, that would be the total pressure. And the total pressure in the air, for example, is 760 millimeters of mercury at sea level. So we call each of these individual pressures, like for oxygen, for nitrogen, for CO2, etc., we call those partial pressures because oxygen makes up just a little portion of the total. So this is a table from your textbook showing us the approximate makeup of what's in the air at sea level. So nitrogen, like a lot of the air is nitrogen gas. Oxygen gas is about 21-ish%. CO2, not that abundant. So if we add up all of those things, then you get 100% in total. The partial pressure of oxygen is 159, and we got that number by just multiplying the partial pressure of, the percentage here. This is like, let's say it's 21% multiplied by 760 millimeters of mercury. If you care about math. So why do we care about this? Why do we care that each gas has its own pressure? The law of partial pressures aids in figuring out how oxygen and carbon dioxide move between the atmosphere and the lungs, between the lungs and the blood, and between the blood and the tissue cells. So Dalton's law influences how O2 and CO2 move. That's really important because gases will always go from the area where partial pressure is higher to the area where partial pressure is lower. Okay, so that's Dalton's law. We're always going to go to the area of lower partial pressure. The other part of this slide is called Henry's law. Henry's law is the idea that gases get dissolved in liquids proportionally to their partial pressure. So that means if the concentration of a gas is greater, there's more of that gas in the liquid. Henry's law also depends on solubility. So, for example, CO2 is 20 times more soluble in water than oxygen. CO2 is way more soluble in water. And oxygen is way more soluble than nitrogen, for example. So that means that CO2 is more easily soluble in water, but oxygen less so, and not so much at all for nitrogen. Henry's law is also influenced by temperature. If there's more temperature, like hotter temperatures, that means there's usually less gas entering. I think of Henry's law as being like the higher the partial pressure, the more we can shove into whatever liquid it is. So I think about it like if you're opening a fizzy drink, like a soda, sparkling water, something like that. So how they get those bubbles in there is because they put lots and lots of CO2 in there under high, high, high levels of pressure, and then it's sealed, right? But when you open that bottle, then you notice all of those bubbles. So when before you open that bottle of soda or sparkling water or whatever, it looks kind of flat. It doesn't look like there's bubbles in there. But when you open it, that decreases the pressure in the bottle, and that's when you see those bubbles because that's the CO2 bubbles trying to escape now that the pressure is lower. Because a lower pressure means that we can't get as much stuff in there. So I think of Henry's law as more pressure means we can put more stuff in it. And more stuff, meaning more gas. This is a picture from your textbook, and before we look too much into it, I'm going to draw some pictures. This picture's from our book. It's showing us how partial pressures affect the movement of oxygen and carbon dioxide. The thing to remember here is that when oxygen, or when air rather, is inspired, breathed in, the thing to remember is that gases go from the area where partial pressure is higher to where partial pressure is lower. So when we're looking at in the blood, so let me draw an alveolus. There's my alveolus. Here's my blood vessel. So the flow of blood is going this way, just so we can track. On this side of my picture, this is deoxygenated blood. On this side of my picture is oxygenated blood. So as blood flows through here, the partial pressure of oxygen, partial pressure of O2, that's the shorthand, is around 40 millimeters of mercury. The partial pressure of CO2, around 45-ish millimeters of mercury. And remember that blood is flowing this way, so we're about to pass the alveolus. As air is inspired, that air that's inspired comes in with partial pressure of oxygen at about 100 millimeters of mercury, while the partial pressure of CO2 is around 40 millimeters of mercury. This is supposed to be 104, give or take a little bit. So we know that from those laws we just talked about, those properties of gases, we know that a partial pressure that's higher is going to be motivating that gas to move to an area where the partial pressure is lower. So 104 is a bigger number than 40, so oxygen wants to enter the blood. And that's exactly what we want to happen, right? So then oxygen will want to enter the blood. And then conversely, 45 is a bigger number than 40, so CO2 will want to leave. CO2 will want to leave the blood. Once we leave the area of the alveolus, now do you see how there's more oxygen in this blood and there's less CO2? So those partial pressures that were on the deoxygenated side, they change. That partial pressure of oxygen changes to about 100 millimeters of mercury, while that partial pressure of CO2 changes to about 40 millimeters of mercury. So what happens is this deoxygenated blood comes in with our partial pressure starting a little bit lower for oxygen, a little bit higher for CO2. And then that inspired air comes in with its own partial pressures. We proceed to equilibrium. And then as we leave the oxygenated blood side, that oxygen is now higher in the blood, that CO2 is now lower. And this is everything that's happening right here. That's what we're drawing right now, is this stuff. How quickly and how much external respiration, gas exchange at the alveolus and the pulmonary capillaries, it depends on a few factors. The first factor is the surface area and the thickness of that respiratory membrane. So the surface area and the thickness of that respiratory membrane. So surface area, like how much surface area is there? Is it a lot? Great, that means more gas exchange. Is it a little? Not so great, less gas exchange. How thick is it? A thicker respiratory membrane means that it takes longer for gases to diffuse, which means that gas exchange or external respiration is slower or less efficient. So when we're thinking about diffusion, shorter distances are always better. So increasing that distance by increasing thickness, that's no bueno. The next thing is called ventilation perfusion coupling. Ventilation perfusion coupling. Ventilation is the actual movement of air like in and out of the lungs, and then perfusion is the passage of the gases into and out of the blood. These processes must match up to each other so that we have like optimal gas exchange. This can be done by adjusting, changing diameter of the arterioles that serve the lungs or the bronchioles. But we can also adjust the diameter of the bronchioles. Adjusting both of those things allows for more synchronized perfusion and ventilation. This isn't like a perfect process, doing all of these things, like adjusting the diameters of the arterioles and the bronchioles, because there's stuff that hinders ventilation perfusion coupling, things like gravity, how much gravity is pulling on certain lung tissues, the mucus level in certain areas of the lungs or the respiratory tract can affect this. But overall, this process of changing those diameters of the arterioles, of the bronchioles, it does a good enough job. Here's an example of how surface area can affect respiration. Surface area can affect respiration. And that's at the level of the alveolus, the external respiration part. So what we're looking at is we have a picture of a normal lung, and we're looking at the alveoli here, how much space. Do you see how there's lots and lots of surface area for gas exchange? This is a lung with emphysema, Emphysema is like enlarged chambers in the lungs. Again, at the level of the alveolus, this is the same magnification level. A lot less surface area, which means a lot less gas exchange. Emphysema is a disease that's commonly caused by smoking tobacco, but there's some other causes for it too. But just know that there's less surface area, which hinders the efficiency of gas exchange. And one of the symptoms of emphysema is shortness of breath, which means like you're feeling that shortness of oxygen and too much carbon dioxide in the blood. Okay, so that's pretty much external respiration. So far what we've done is we've talked about pulmonary ventilation in a previous video. We talked about external respiration, and now we're going to skip this one for now. We're going to circle back to it. And then we're going to talk about internal respiration. That's what we're going to talk about next because it's kind of like or kind of like external respiration. So back to the same picture I showed you before. So back to the same picture I showed you before. So I'm going to draw you a picture and then I'll show you what we're looking at. So here, if we have the cells of our tissues, these are tissue cells. And we have a capillary coming through, and this time blood's moving this way. So on this side, we have oxygenated blood. And on this side, we have deoxygenated blood. What we're looking at is that the partial pressures still motivate the movement of oxygen and carbon dioxide. So when we're looking at oxygen, the partial pressure of oxygenated blood reaching the tissues, give or take a little bit, partial pressure of oxygen is about 100 millimeters of mercury. The partial pressure of CO2 is around 40 millimeters of mercury. In the tissues, though, the partial pressure of oxygen is about 40. The partial pressure of CO2 is about 45. So this is the same story as before, but it's the reverse. Oxygen is now motivated to leave, while CO2 is motivated to enter the blood. So that means when we leave on the flip side of this picture, when we leave as deoxygenated blood, that means that our partial pressure of oxygen will decrease. So partial pressure of oxygen will be around 40-ish. And the partial pressure of CO2 will be about 45-ish. Because oxygen is left, so we go from 100 to 40, and then CO2 has entered the blood, so that we increase from 40 to 45. So what we're looking at is this bottom part of the picture. So we have blood leaving the lungs, entering the capillaries. Here's our partial pressures in the tissues. And then here's that blood coming back and leaving into the lungs. So it's the same story, just backwards. All right, now let's talk about hemoglobin. Gas transport in the blood is a bit different than gas exchange at the capillaries. But anyways, we're going to talk about oxygen. Oxygen is the major player, so I'm going to talk about that first. The first way that oxygen can travel through the blood is with hemoglobin. So oxygen and hemoglobin, that's how we've talked about oxygen transport in the past. And remember that hemoglobin has like 4 subunits with a heme on it. And that's the major component of red blood cells. Oxygen is much less soluble than water in CO2, so it's really helpful for oxygen to hop onto hemoglobin for a ride. And so hemoglobin can hold up to 4 oxygens at once. It can hold on to up to 4 hemoglobins or hold up to 4 oxygens at one time. And this is super reversible. What that means is that oxygen can hop on hemoglobin and pop off as needed. And this is how like 98.5% of oxygen is transported. So 98% of oxygen is transported in this way. So what this looks like is that hemoglobin, which we call HB, will bind oxygen, and that will give us HBO2, just for shorthand, like hemoglobin with oxygen on it. How much hemoglobin can bind with oxygen depends in large part on 2 factors. One, on the partial pressure of oxygen, and the other is how saturated or how full of oxygens hemoglobin is. Hemoglobin's affinity for oxygen changes as it picks up more and more oxygen. So, hemoglobin with 1 oxygen on it would have a different affinity for oxygen compared to hemoglobin with 3 oxygens on it. Affinity is just how much that molecule wants to grab on to the gas, oxygen, for example. Okay, so first let's talk about partial pressure. When partial pressure PO2 is high, this makes hemoglobin gets more saturated. So there's more oxygen on those hemoglobin molecules. When partial pressure of O2 is low, that means that hemoglobin gets less saturated. We call this oxygen offloading, which means that hemoglobin is getting rid of that oxygen. And that's good, actually, because we need to drop off oxygen at the tissues, right? Other factors can also affect how oxygen is transported. So all of these factors down here affect hemoglobin structure and also its affinity for oxygen. So increasing all these things, so if all these things increasing all of those things means that hemoglobin's affinity for oxygen will be lower. Hemoglobin's affinity for oxygen will be lower, which means that it's harder for hemoglobin to grab on to oxygen in the blood. Again, remember that this is going to promote offloading of oxygen or getting oxygen off of hemoglobin and wherever it needs to go. So these factors are temperature, so how warm or how cold. Blood pH is how many hydrogen ions are around. So remember that pH is like how many hydrogen ions. More hydrogen ions means more acidic, right? Um, the partial pressure of carbon dioxide, and then this molecule BPG. BPG um, is stands for 2,3 bisphosphoglycerate, or BPG for short. BPG is a substance that's produced by red blood cells during glucose metabolism, just so you know. Anyways, but so if we increase all those factors, then that'll make hemoglobin's affinity for oxygen lower. So the flip side is true, is that if we were to decrease all of these things, that would make hemoglobin's affinity for oxygen higher instead. The last thing that I haven't talked about on this slide is the Bohr effect. So the Bohr effect is, oops. The Bohr effect is there's more oxygen offloading due to changes in pH and the partial pressure of CO2. We'll get into that again in a minute. Okay, so all of this oxygen transport stuff. This is a graphical representation of what I was just saying. What these graphs are showing you is that here, this like purplish line is normal. Normal body temperature, normal CO2, or normal hydrogen ions concentration. When these values change or deviate from the purple value, from normal, that means that we can increase how much oxygen is saturating hemoglobin. So, percent of oxygen saturating hemoglobin, that's the thing that's on the y-axis. How much oxygen is hanging out on that hemoglobin. So if we shift this graph from normal to the right, that means that we would increase body temperature, for example. Then we see there's less oxygen on hemoglobin. So if we shift to the right, we see there's less oxygen on hemoglobin. If the graph shifts to the left, so we have a lower temperature, we have less carbon dioxide, for example, we see that we have more oxygen hanging out on hemoglobin. More oxygen on hemoglobin means not as much as being offloaded for use in the body. Okay, so CO2 is next. CO2 is produced in our tissue cells, and then the blood transports that CO2 to be released into the alveolus, and then that CO2 leaves into the atmosphere. CO2 can be dissolved in plasma, and it travels through blood that way, about 10%-ish or so. CO2 can travel through the plasma, dissolved. CO2 can also catch a ride on hemoglobin. When CO2 binds hemoglobin, it's called, so CO2 plus HHB, that's called carbaminohemoglobin. Carbaminohemoglobin. It doesn't compete with oxygen binding spots because CO2 binds hemoglobin at a different spot than oxygen does. Anyways, the partial pressure of CO2 also influences if hemoglobin holds on to CO2 or offloads it based on that partial pressure gradient. So same thing as oxygen. If partial pressure rises or partial pressure lowers, then that motivates how hard hemoglobin is holding on to that CO2. The other thing that can happen, which is the thing that happens most of the time, is that CO2 can travel as bicarbonate. So CO2 travels disguised as bicarb. And bicarb, this reaction to make CO2 into bicarb, mostly happens inside of red blood cells. So here's my red blood cell. Red blood cell. What happens is that CO2 will come in here. CO2. It'll combine with water. Then it forms this thing called carbonic acid, H2CO3. There's an enzyme in there. And the enzyme in there that makes this reaction really fast. Enzyme. I'll zoom in on this. There's an enzyme, it's called carbonic anhydrase. Which is found in the red blood cell. So if this reaction would happen in the blood, it wouldn't use the enzyme, so it'd happen a little bit slower. But then that carbonic acid, this is carbonic acid, it dissociates into hydrogen ions and bicarb. So this is where that CO2 is hiding. Do you see CO, and then there's 3 of them, so there's, you know what I mean, CO2. And it's just hiding in there, right? This reaction can lead to an accumulation of hydrogen ions in the blood, which can lead to the Bohr effect. Okay, the Bohr effect, that's the one where hemoglobin decreases its affinity for oxygen if the blood is too acidic or if there's too much CO2. And remember that we don't always want hemoglobin to hold on to oxygen or to carbon dioxide, right? Because more CO2 being around means that oxygen can be released more easily. And we also need to use it in the tissues and all that kind of stuff. Okay, so bicarb, it can be moved in and out of the red blood cell into the plasma. And how this happens is this bicarb can move out into the plasma. That bicarb moves into the plasma, but notice that by moving that bicarb to the plasma, we've lost a negative ion in that red blood cell. So to make up for that negative thing that we just lost, what happens is that a chloride ion will enter the red blood cell. And that chloride ion kind of exchanging, you see how we lost a negative ion, but we gained a negative ion. That is called a chloride shift. Chloride shift, which is done to keep the charge of the red blood cell the same. So it keeps the charge same. And likewise, if bicarb wants to enter that cell again, then that chloride will just leave. Chloride shift again. So this reaction is something that's really important. So we're going to talk about it again on the next slide. But the big thing to know is that bicarb, that's how CO2 travels in the blood. And it's done because of this. Okay, so blood buffering system. One of the really important things to know about this reaction is that CO2 and water, they act like a buffering system. A buffering system is something that resists shifts in blood pH. So it resists changes in pH. And how this works real quick is that if hydrogen ions become too abundant, so they're too high, which means that like there's too much acid, the pH is too low, what happens is that this hydrogen ions will signal this reaction to shift this way. So hydrogen ions will combine with bicarb, will make carbonic acid. If hydrogen ions become too low, so things come too basic, then that carbonic acid shifts the reaction this way to release more hydrogen ions. So carbon dioxide then, because that's where all this stuff comes from, is really important for regulating the pH of the body. And we do this in the respiratory system by altering our rate and our depth of breathing. So, regulating blood CO2 is really important because we can regulate pH. And we do this by altering the rate and the depth of our breathing. We're going to talk more about this in the lab, but we'll also talk more about acid and base balance when we get a little bit more into the renal system, too, which is also part of this unit. Lastly, let's talk about hypoxia. Hypoxia is when the oxygen in the tissues is just in short supply. There's just not that much oxygen around. There's a lot of potential causes for hypoxia, so I'll touch on a few that are in our book. The first is anemic hypoxia. Anemic hypoxia is when we have low red blood cells, or anything that is anemic, right? So we've talked about anemia in the blood chapter, right? So it could be less red blood cells, poor red blood cell oxygen transport due to like abnormal red blood cells, low hemoglobin, any of those types of things. So low red blood cells, etc. And the operative word in this one is anemic, right? The next one is called ischemic hypoxia. Ischemic hypoxia is when oxygen transport or oxygen circulation, or wait, blood circulation is what I mean. Blood circulation is impaired. Or it's cut off. So that tissue is deprived of oxygen. So naturally, hypoxia occurs. We don't have enough oxygen being delivered to those tissues. The next one is hypoxemic. Hypoxia rather. Hypoxemic. And this is when the partial pressure of oxygen is too low. When the partial pressure of oxygen is too low, that can be a result of like poor ventilation, it's not working, poor perfusion, we're not getting that oxygen into the blood. We're just like not in an area where there's enough oxygen around. And then the last one, I think, is probably the most unique one on this slide. It's carbon monoxide poisoning. So carbon monoxide is an interesting one. Carbon monoxide is CO. It's really interesting because carbon monoxide is a gas. It's a colorless, odorless gas. And it has a really high affinity, high affinity. Has a high affinity for hemoglobin. A lot more than oxygen. So given the choice, hemoglobin will bind carbon monoxide rather than oxygen. This really interferes with oxygen transport because carbon monoxide is taking up those same binding sites that oxygen would have. So there's just not enough space on the hemoglobin for oxygen to hop on because carbon monoxide has such a high affinity, or hemoglobin has such a high affinity for carbon monoxide. Symptoms of carbon monoxide poisoning are feeling like confused and having like this big throbbing headache. And for treatment of carbon monoxide poisoning, patients are usually given for treatment. Patients are usually given 100% oxygen, or they're given hyperbaric therapy. Hyperbaric therapy. Hyperbaric therapy is the idea that patients are subjected to higher than normal pressures. And remember that those properties of gases state that more pressures promote stuff entering the blood. So, more pressures in a hyperbaric chamber means that we're promoting oxygen to enter that blood. And this is continued until oxygen levels normalize. So, that's what I have for this video. I look forward to seeing you in the next one.